Go.
Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and with me as always is...
Robert Moore.
So, Robert, we are in episode number 2, season number 2.
Yes, indeed.
So,
Cruising right along.
2 and 2.
2 and 2.
We're broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. If you have any questions during the podcast, please feel free to use our live chat and give us any comments or questions that you may have, and we'll stop the podcast in the middle and answer your questions to the best that we can.
Kill it cleanly, and we'll think about it for a while and then come back.
on.
No, we won't do that.
As a disclaimer, anything that Robert and I say are our own personal opinions and not necessarily those of the university or anyone affiliated with the university. And with that out of the way, Robert, what do you think of now winter is finally here in North Dakota?
It's kind of strange because it's like winter came down further south than it did here. It's like so friends of mine showed me, he was on the show, James Owens, showed me some pictures of Knoxville, Tennessee, and they're under more snow than we have here.
Yeah, we don't have much snow. We only got a couple
of snow.
Yeah.
But, we're down around 0.
Yeah.
So
Fahrenheit. Yeah.
So
I know overnight temperatures have dropped as low as I think it was minus 24 one evening. I noticed
right.
Middle of the night. Well, just a couple hours before daylight type of thing. But that's typical for this time of the year, for where we are. So
we've been fortunate that it's been warmer than it typically is, and looks like it's headed back there.
Yeah, and the nice thing is by this weekend, I think Sunday, where the temperatures are supposed to get above even freezing.
Mm-hmm.
So we're up to like 32, 33, 34 Fahrenheit.
Which, folks, that's really warm for here, for those of you who might not be here.
Yeah,
that's
so
really warm.
We'll see how long that lasts, of course.
Yeah.
If it can last long enough, by the time we get to the end of February, we got a beat, really.
Yes.
Because we do feel, the warmth coming back for certain in March.
In March, yeah.
But we'll see. We'll see how
things.
See how it goes. Now, Robert, of course, we talk about a lot of the science that's new that happened in the recent, 7 days since we've been on live.
Right.
And there have been a couple of things that have just came out recently. In fact, there's been a meeting that happens twice a year of the American Astronomical Society, and it just wrapped up last week in New Orleans. And so there are a lot of information that has come from me. I know you're going to say it the right way, right?
Yeah, I'm going to say it's New Orleans. So
for the rest of us who are not Southerners.
Yeah, who didn't grow up in the area.
It's New Orleans.
Yeah.
Anyways, so we'll talk a little bit about some of that stuff that came out. But the one thing that caught my interest is actually not something that's related directly to astronomy, or unless you're thinking about planet Earth itself.
Okay.
And this was a study that showed evidence that photosynthesis, so that is using sunlight to make energy for plants.
Right.
Actually, there was fossilized evidence of that occurring here on Earth about 1.75 billion years ago.
That's a lot sooner than what had previously been thought.
Yeah, so you want to bring up our first slide and we'll show the evidence for that. So here's a paper that was submitted to Nature describing these results. So this is something that came out recently, a few days back. And on the right, you can see, so just like an image of what it would like in early Earth, let's say when we're in the time of the plants and planting swamps. And
I will point out that at this time of the planet Earth, there would have been no ferns or anything like that because there would have been nothing on the land.
Not at 1.75 billion years ago.
Barren rock.
So when you think of photosynthesis, I guess that's fair to use the image that's in the top right. Example of photosynthesis, I mean.
Yes, as an example of photosynthesis that we're all going to relate to, that's a pretty good example.
Imagine if Venus was like that now.
Oh.
Like that's what you would encounter if you landed on Venus. You'd see what you see there in the upper right.
They did back in the 50s and 60s, because I remember as a kid reading a short story by, I forget who it was, where Venus was this tropical jungle.
Yeah, well, I remember even Carl Sagan, he's a planetary scientist by training, had written, I think, a paper on what is the surface temperature of Venus. And based on the observations that they could make at the time, looking at how much energy comes off the planet and how much, you can calculate that it would absorb from the sun given its distance and so on and so forth. They come up with estimates of very high temperatures that it would not be a lush jungle like you see here. And
but it's covered in clouds.
Right, so it's hard to know until you, but till you go there. And of course,
Yeah.
the Soviet Union sent landers to the surface of Venus
Mm-hmm.
and was able to look around to see what's there. It was nothing but a desert-like area, extremely
Right.
hot. In fact, landers, I think the one that lasted the most on the surface was about an hour and 15 minutes roughly. Or
Something
something
like
that,
that,
right?
yeah.
75 minutes or up.
It-
Yeah.
Yeah, it's hot enough to melt lead, so it was definitely melting the soldering of the electronic circuits and things like that.
Yeah, and from the point of view, okay, should we go back to Venus and get more detail? I mean,
Oh, absolutely.
we want to go and sample the soil, and we can do that like right there on the surface. We can send up portable laboratories. So like we've done for Mars, scoop up some of the soil, put it internal to some lander, have rovers.
Flying craft are easier on Venus than it would be here on Earth.
So there's like the Dragonfly mission
Right.
that's part of Perseverance that's running on Mars now. And they send that up, every once in a while. It's made more than 60 sorties, as you would say. And so that gives us a new perspective, new way of looking at Mars, especially if it's guiding where the rovers can go, can look for hazards or look for interesting geological features and so on.
Right.
Yeah, but you're right, to do that on Venus is even easier from that point of view. But of course, the thing we have to get over is the extreme heat and pressure.
And the harshness of that atmosphere, because it is sulfuric acid and phosphenes and things like that are just harsh on equipment, even beyond the temperatures and the pressure.
Yeah, and so there's been a lot of work that's done since those early days of landing a spacecraft on Venus that, as far as I know, we've developed electronics that can survive the high temperature and pressure.
Well, we're working on them.
Yeah, I think we're almost there, is my understanding, right? I think if somebody, like a government agency or some private rich person, if they would fork over a large amount of money,
We can
because it all
possibly
comes
do
down
it.
to money. Yeah,
It does.
exactly. Then we'd be able to do it probably, within the next decade maybe.
Right.
And have some good quality sort of spacecraft on the surface of Venus, staking it out.
Yep.
Venus is important to us, not from the thing where Venus's mass is essentially like the Earth, and its size is essentially like the Earth. So in other words, it's a twin from that point of view, but it's not a twin for the conditions that exist on the surface of Venus.
Right.
And you wonder, was Venus always like that, the way it is now, where if you put like 16-inch pepperoni pizza and laid it out on its surface, you don't need an oven, it would be cooked in a few minutes because of the extreme temperature. Why did it get that way?
And that's a very good question.
I think that's the question when it comes to comparing Venus to Earth. So, Robert, as you know, when we talk about the solar system, there's this comparative planetology. Is that the name of it?
That is one of the classes. Yeah, I've taken that one.
So we try to compare the Earth to all the other, major planets in our solar system to see what they're like, how are they different, why are they different, if we can figure that out.
Right.
And that leads, down this tree of questions that can branch out into various directions. People suppose that it's a runaway greenhouse effect for Venus.
Right. I'm one of the ones a little skeptical of that. That's the generally accepted idea is that it developed for whatever reason a high CO2 concentration in its atmosphere. The atmosphere, due to volcanism, was increased so that it, in other words, it's a now thick CO2 atmosphere, and there's no evidence of water or anything, plate tectonics or anything like that going on. So that's been accepted that it's just that buildup of CO2 in the air, in its atmosphere, that caused it to get that way. But I think it's the lack of water, personally.
Now, when we talk about surface temperatures of planets, I guess a good way of thinking about it is, follow the energy. So if you have some planet like the Earth, let's say, as an example, and the energy that it receives then on its surface is obviously the energy that comes from the sun.
Right.
Ultimately. So you have heating by the sun during the daytime, and let's say it's a nice clear day, no clouds at some location.
Right.
And so you're building up the energy on the surface, and that energy has to go somewhere. So during the night, then, that energy gets re-radiated, as we say, out in the space, mainly in infrared. Now, if you block the release of that infrared light, for example, by putting lots of carbon dioxide in the atmosphere, that would make the atmosphere, if you put enough of it, it would make it essentially opaque. To the emission of infrared light, that energy then can't get away from the Earth. It is trapped and
Right.
on the surface of the Earth between that atmospheric layer of carbon dioxide and the Earth's surface. And then, of course, in the daytime, you add more energy to that
Right.
equation, and that energy can't get out. So overall, there is a net increase in energy on the surface of the Earth.
And what happens to the CO2 atmosphere is that it absorbs, but then it re-radiates at a longer wavelength infrared. The heat stays here instead of being reflected and dissipated into space.
So at some point, as we learn in chemistry, when you think of chemical reactions, if you've taken chemistry in high school, that it eventually would reach some equilibrium.
Right.
And that equilibrium would determine what is the average or mean surface temperature.
Right.
So on Venus, it's extremely high. And associated with that is a global circulation, that is winds that are extreme, right? Very fast winds compared to what we have here on Earth. And that causes an actual equilibrium of the temperature around Venus itself.
Right.
So the daytime temperature is just as hot as the nighttime temperature.
Yeah, there is no cooling at night on Venus.
Right. Now, how did it get to that point? And we alluded to the fact that if you have a tremendous release of carbon dioxide into the atmosphere, that could potentially do it. And I'm sure there's probably other ways, right? And you mentioned, lack of water.
Lack of water. You see, what we don't realize here on Earth is a lot of the CO2 is taken out of the air. Oh, yeah, by plants. Well, yeah, but by also rock formation. And that is then subducted into the mantle with the plate tectonics. And that subduction takes the CO2 down into the mantle instead of it being left here to slowly but surely gather up. So without plate tectonics, and the reason I mention water is because water lubricates a lot of that type of motion. So without that, there's probably a reason the plate tectonics didn't start, which would have taken CO2 out of the circulation, would have circulated into the mantle. And, is that what happened? Who knows?
Well, when you talk about the carbon dioxide, I think you mentioned being taken underground by the conveyor belt, right? That's almost like, if you want to phrase that into modern, verbiage, that's like the ultimate carbon capture experiment, is it not?
That's exactly, it's the carbon cycle, and it's called carbon capture.
So it's nature's carbon capture.
It's nature's
right?
carbon capture.
Yeah, and that's what we're trying to invent on a global scale, if we want to say that, from humans.
We're trying to figure out ways to do it technologically because
Right.
we're putting a lot of CO2 in the air.
Well, that's the thing, you wonder whether Venus ultimately came because of the huge abundance of carbon dioxide in its atmosphere. If the Earth follows a route where we put a lot of carbon dioxide in our atmosphere, then people are worried about the fact that we could have this runaway greenhouse effect and ultimately end up, even if it was a slightly different way of getting there, ultimately ending up in the exact same place that Venus is today.
And that's highly unlikely, but here's the thing. The real issue is not that the Earth is warming, because as so many people like to point out, that's happened throughout history, warming and cooling and warming and cooling. But it happens when the Earth does it, it happens on a scale of 10,000 years or longer. It's happening on the scale of 100 of years or 200 years right now. You can't adapt to that. So
Yeah, it's too rapid. So we can talk about what is the amount of carbon dioxide that's released naturally, let's say on the surface of the Earth through volcanoes is one method.
And
Is that the primary method then, Robert?
there's volcanoes. There's the smokers at the bottom near the spreading ridges in the oceans.
So is that like the Mariana Trenches type stuff?
No, that's
or-
a subduction zone.
Okay.
But there's these spreading centers
like the Mid-Atlantic Rift or
like
something?
the
like that?
Mid-Atlantic Ridge and things like
Okay,
that.
ridge. Okay.
So yes, most of the CO2 being released is through volcanic nature, but it's not necessarily volcanoes.
So if you compare the amount of yearly release of carbon dioxide through volcanoes, which we can't control here on the Earth,
Right.
obviously, how does that compare to what human activity puts out into the atmosphere?
Despite what a lot of people want to think, we are actually putting 100 times the amount of CO2 into the air as comes from natural sources. You can go check that out. That's in the literature. That's peer-reviewed science. Okay? You can believe people who have a vested interest in that not being true. But the truth of the matter is, we are putting 100 times the amount of CO2 into the atmosphere as natural sources, including volcanoes.
And that's where the problem lies, right?
That's where the problem lies.
Now, is it fair to say that we don't know in detail, because atmospheric science is what we're talking about here, is very complicated. There are a lot of
Yes.
different types of reactions that interconnect, that depend on each other, and it's hard to model it exactly.
Right.
But what we do know is that amount of carbon dioxide pumped into the atmosphere is not a good thing.
It's not a good thing. Even if we're a little wrong on that, the issue is, well, how do we know that? Well, we know how much CO2 cars put out. We know how much CO2 factories put out. So we know how much we're generating. We also can go measure a volcano and determine how much is coming out from that. And we can compare. We know there's this many volcanoes active on Earth. This is not a hard thing to actually measure and do. And so, yeah, the problem is we're digging up essentially carbon that was sequestered back in what we call, I think it's the Cambrian period. And we're burning it and putting it back in the atmosphere. Well, we know from chemical reactions that form minerals that period in Earth's history was about 20 degrees C warmer than it is now. So think about the average temperature across the Earth being about 20 degrees Celsius higher than it is now. We're talking about the devastation that'll come back from 6 now to nearly 4 times that amount. That's what we're doing.
Yeah, 20 degrees increase in Celsius, that's almost like what's in this room that we're in right now.
Right? That's why I keep rubbing my forehead and everything.
Well, yeah, the heat in here is stifling. We're actually boiling.
It's stifling in here.
But can you give us an outline, Robert, of some of the major events, let's say, that happen on the Earth when we talk about the arrival of life and how things change? Because I know in the very early days, the amount of oxygen in the air was minimal. Compared to what we have today.
And in fact, some of the greatest extinction events came about because oxygen for a long time was a waste gas.
So it's like a poison to life forms, right?
It was like drinking your own urine and eating your own poo.
Right.
These things were dying in their own waste product, which was oxygen. Now, this is what a lot of people don't realize is that oxygen is nasty, nasty, nasty stuff. If you hear about free radicals that kill us, they're talking about oxygen. Okay? We are slowly burning. We're, 75-year fire, essentially.
Right.
And so oxygen is nasty stuff. It combines with everything. It's very reactive. It's just nasty. So this stuff was giving off oxygen as a waste product. It would build up in the atmosphere, and they'd die off. And then they'd come back, and then they'd die off. And for a while there, the oxygen would also be taken up by taking iron out of the ocean, out of the water, and combining it. So you may have heard in Minnesota, because there's some famous examples of it, of the banded iron formations. Mm-hmm. That's what they're talking about, is these oxygenation events where the microscopic life would build up, produce a lot of oxygen. It would then react out of the air into the rocks and such as that. So that's how things got started. Then came along some organisms who learned to utilize that oxygen.
So it's the slow evolution of creatures that could actually turn that poison into useful products but then now they require oxygen.
And now they require oxygen. So, we think of plants as being the source of oxygen, but in reality, they use oxygen too. They just produce more than they use. So right. That's what's going on. So getting back to our story here, it's always been debated as to when photosynthesis kicked off. And we knew that it got a reasonably early start because of some things called stromatolites, which are structures built by cyanobacteria. And they form these nice little layered lumps because you get the bacteria forming, and they die off, and they've formed a bigger mat around that inner mat, and so forth and so on, until you get these nice, large, roundish structures. But what these people found is evidence of cyanobacteria that go back earlier than what we thought the earliest stromatolites were.
Right.
And in fact, they're talking about 1.75 billion years, which would have been about a billion years, billion and a half years after our first evidence of life processes.
Right. And this
On
is
Earth.
so. If you go back 1.75 billion years into the past, do you know what the oxygen levels were like here on Earth?
They would have actually been fairly high.
So this is after what they call the Great Oxidation type
Yes.
of event.
This would have been after all of the iron had been oxidized out of the water, out of the land, and turned into Fe2O3 or FeOH,
Right.
such as that.
Right.
So Mizuho Schwamm brings in the methane, absorbs, reflects much more CO2, as you know. Yes, we were talking about the greenhouse effect from CO2.
Right.
Methane or methane is actually much worse, much stronger greenhouse gas. Okay, so we're not producing much methane. Well, the problem is if there's much of the methane on Earth is involved in what we call methyl clathrates in the ocean. So if the ocean warms up enough, those get released, and I ain't gonna lie, folks, it's game over if
It
that
adds
gets
to the
released.
problem dramatically. Right?
That adds to the problem
Yeah.
horrifically, to be
Right.
honest.
Right.
So yeah, keep in mind that CO2 is not the only problem. Methane release is massive. Methane release causes a mass extinction. So methane coming out of the oceans is going to be a really bad day. So anyway, yeah,
So these bacteria, then if they're participating in photosynthesis.
right.
So they have chlorophyll like plants then in that case, or what do they have instead?
I don't know that it's necessarily chlorophyll. It's you see that word thylakoids.
Right.
They have certain alkaloids which are photoreactive and can absorb in the energy of life and of sunlight and use that to convert CO2 and water into longer chain carbohydrates, sugar.
So they do in general the same type of process that the chlorophyll does.
But I think this would have been earlier than necessarily chlorophyll.
Right.
But there are a lot of similar type of molecules out there in this class of thylakoids. And I think these probably were that. It was chlorophyll was a product of a particular type of bacteria that was eventually incorporated into other single-celled organisms and became the chloroplasts that modern plants have.
You know what I'm getting at is when we look at other planets looking for signs of life,
Right.
what do you want to search for? And if you restrict yourself to just chlorophyll type, you might be missing a whole avenue of the energy conversion processes from sun.
Right. And so looking for thylakoids is a good thing in general. But, we've mentioned the other things to look for too, methane, which is highly reactive and will be taken out of the atmosphere fairly readily by ultraviolet light. Oxygen, which reacts with everything, so it's quickly removed from an atmosphere. So sustained oxygen, sustained methane, presence of thylakoids, thylakoid molecules and things like that are exactly what we would be looking for in the atmospheres.
So it's not just one thing in particular. I mean, we did remember the possible detection of the CFCs, the technosignatures. But in general, you're going to look at multiple things, right?
Multiple
Not just
things.
relying on just detection of one single item or
It's
element.
we've mentioned it before. If you have one thing that's indicating an answer, that doesn't mean that that's the answer. But you start getting 4, 5, 6 things pointing at the same answer, I'm pretty confident now that that's the answer.
Yeah, you have to build up a case, right?
Right.
So you let the data kind of tell you where to go in this kind of thing. And the more evidence that you have for an existing idea or hypothesis, whatever, the more closer hopefully you are to the truth, to reality in that sense.
That's the end result, yes. So, on our cyanobacteria here, they found, as they show in the picture on the bottom right, they found fossilized shells of these things, and they're thylakoid bacteria. So, yeah.
Yeah.
So Mizuho Schwamm again, the problem is we don't know how much methane is released to the air. We don't. How much methane does life produce? How much is produced by volcanoes? How much is produced by natural processes?
Cows.
Cows. Well, cows would be life. So
Right? But that was brought up as a major source, right?
Right.
Cows.
and it's like, no, there's plenty of natural sources out there
Right.
without bringing in cows into the picture.
But that was talked about, right? It's
It
a
was.
serious contribution.
It
so we
was.
should eliminate all cows or something, right?
Right. And it's like, no.
Everybody go on a plant-based diet and get rid
Yeah.
of cows.
It
Totally.
might be better for us to do that.
We
in the
live
long
longer.
run, but
Whether or not we enjoy our life, even though we
Right.
live longer, that's the other question, right?
that's it.
Yeah.
So, yeah, so that's what's going on with this. And really, all it did was push back the date of that arrival. As I mentioned, 3.5 billion years ago, we have evidence of life, chemistry going on. And here we are, before it was thought to be around 600 to 700 million years, so less than a billion years ago, that photosynthesis started. And here we have evidence that pushes that back to about 1.7 billion
Yeah.
years.
The greatest mystery in all this really is how do you go from something that's not alive to life itself?
And we don't have a complete answer.
If I was just starting my career over again and wanted to get into biology and talk about these kind of fundamental issues, that'd be the one I'd be looking at
Right.
as most interesting to me anyways.
And as if you go do research and dig into it and into the published papers, you'll find that we do have some answers leading that direction. Do we have a complete answer? No. But it's not like we don't know nothing. We know nothing. We know quite a bit. It's just how it all was put together.
Well, if we knew everything, then we'd be done, right?
Well, we'd be out of a job.
Yeah. So there's lots of work to be done in different areas.
I'm glad we keep finding new things because that's job security.
Well, you think that the sake of where does life come from at the very beginning is very interesting.
Mm-hmm.
But even more so now when we discover all thousands and thousands of these other planets orbiting their own host star, if you were eventually looking for signatures of life, that's one that puts more emphasis on figuring this puzzle out, or ultimately did life come from? Does that mean it's commonplace and, so on and so forth, right?
And I, as we've discussed, we've talked about it, I'm an optimist on that. I think life is going to prove to be fairly common. Complex life, that's another matter.
Well, that gives you, some motivation why you want to do things like the SETI.
Right.
And, listen with a radio telescope and see if you can pick up any signals coming from extraterrestrials.
Right.
Whether they exist or not, and broadcasting on those frequencies that you're listening to or doing some other way of communicating, who knows?
Who knows?
But at least you got to look, because if you imagine you're the first person to try this, I don't know, in the early 60s, late 50s, and you use a decent-sized radio telescope, and you start listening, and all of a sudden you hear signals coming all over the place.
Well, that happened, didn't it?
Well, no, but what I'm getting at is you don't know that could be the case unless you go do the experiment, right? You have to do the observation.
You do the observation.
And it turned out that wasn't the case, ultimately, right? There aren't all these signals coming that we could easily pick up today with our present technology. We haven't found any. But that may not have been the case, right? We had to go do the experiment. You just don't assume, probably it's just us and don't worry about it.
And this is definitely something that you don't stop looking. Do you make it a major project? Maybe not. But you don't not look because the signal may be there for an instant.
Well, it reminds me of the fable of where do you find your car keys if you lost them? Well, you search where at night if you lost them outside. You search where the outdoor light is because that's the only area you can see.
Right.
You don't search all the dark areas because you can't find them, right? You might just stumble across it by accident, but you look for where you can see.
Except if your path to the car was through a lot of dark area, you're kind of silly looking only in the light.
Yeah, so you try to use evidence like that where to increase the probability of finding them.
You look
and you look at areas where you think, based on the knowledge that you have today about how life exists, where would be the good places to look in terms of those exoplanets.
Right. And that's why we do have a bias in exoplanet research to looking at sun-like stars. Yeah. And it is for that reason. We're kind of interested in trying to find ET if he's out there. And so we look primarily at where we know this experiment called life happened.
Yeah, we have an example of just one location, and we have to go and make the best use of that information.
Right.
So it's quite interesting when you think about it. Now, Robert, there's been other results that have been released recently. This is more in the tradition of astronomy and cosmology.
Yep.
And this is a new paper that was submitted by the Dark Energy Survey. And just as a disclaimer, I am an associate member of the Dark Energy Survey. I'm not on this paper. I didn't do any of the work associated with this paper. So what this paper is doing is they're releasing results for 5 years of data. So analysis done on 5 years of data from the Dark Energy Survey, which is a large survey to observe 20,000 square degrees of the sky in the southern hemisphere. And the reason for this survey initially was to try to, if you like, better measure the influence of dark energy in our universe. So dark energy is this accelerated expansion that was discovered back in 1998. And before 1998, if you ask an astronomer, what's the universe doing in terms of expansion? Well, the expansion itself was discovered in the 1920s, put together by Edwin Hubble, using data from various sources and other astronomers as well. The idea is, in a simple model, if we think of an expanding universe, because a universe contains matter and energy, and therefore there's gravity associated with that matter and energy in that universe, and gravity, for this point of analysis, it only comes in one flavor, unlike ice cream, as I like to say. It's always an attractive force.
Right.
So the combined gravitational attraction of everything that's contained within the universe would cause the expansion of the universe to slow down. And a big sort of problem was to try to measure the slowing down accurately enough to determine, for example, if we go into the future, will the universe come to a complete stop and then reverse and start contracting, start getting smaller? The reverse of the Big Bang idea, if you like. Or is there not enough matter and energy in the universe so that the expansion rate may slow down with time, but it never goes to zero, it never reverses?
Right.
So the universe would just continue to expand forever at an ever decreasing rate.
Right.
Or the third sort of unstable position is maybe there's just enough, just the right amount of matter and energy in our universe that as we go forward in time, the expansion rate slows down, and finally, as time goes to infinity, the expansion rate goes to zero. So it neither collapses in on itself nor gets any larger as time goes to huge values towards infinity in the far, far future.
Right.
So which of those three universes describe our universe, describes reality? That was something astronomers wanted to look at and wanted to solve, wanted to come up with the answer to that question. And they essentially worked on it for decades and decades. It's a hard problem.
It's a hard problem.
Yeah, it's not easy. It takes very good observations over large swaths of the sky. And the other thing is you have to make very precise observation. That's always been a problem. You can measure things, but things that you measure are uncertain by factors of 2, and that makes this analysis very hard to determine. So in 1998, looking at what we call Type 1a supernovae. Now, as an aside, what is a Type 1a supernova? Robert, do you want to pick up on that a little bit?
Yeah, I can talk at least a little bit about that. The Type 1a supernova is basically where a white dwarf.
And what is a white dwarf?
A white dwarf is the dead ember of a star, kind of like our sun.
Right, so a low mass.
So a low mass star. And that has a pretty precisely known limit on how big, how massive those can be, because they're held up from further collapse by what we call electron degeneracy pressure. So the electrons are bouncing around at close to the speed of light. Well, there's a limit then. If they reach the speed of light, it can't get any bigger. It'll collapse.
And that limit is about 1.4 times the mass of our sun, roughly.
Right. So Type 1a supernova are where mass is accrued to a white dwarf that's a roughly 1.4 solar masses.
Maximum.
Right. And so eventually that limit is crossed and it collapses and then explodes.
So in other words, if a white dwarf is close to that limit, let's say, 1.3 solar masses.
It's pretty stable at that point, but...
Right, and we know that the sun, so this is what makes our solar system different than a lot of other star systems is that the majority of stars, as far as we can tell in our Milky Way, for example, in our home galaxy, there's not just one star and then a system of planets. There's usually
Right.
two stars in orbit around each other, in some cases 3, 4, and even 5 systems. So the majority of stars are in what we call these binary or multiple star systems.
Right.
And then what happens if you have a white dwarf then that's in an orbit around another star? What potentially can happen to affect its mass?
Because they were formed at the same time, they're probably going to be close, similar masses. So that other star, when it starts dying, expands, becomes a giant star. And if that white dwarf is close enough, it'll start siphoning off the material in that expanding red giant, siphoning off its surface.
Right, so you could have a scenario then, just to be clear, where you have two low mass stars, let's say.
Okay.
Well, you can change that idea, but let's say you have two low mass stars. The one that has the greater mass, so a rule of thumb is a star that has more mass than some other star will go through all of its life phases, life cycles quicker than the
Right.
lower mass star.
I like to put it in terms of like a Honda Insight versus one of the big SUVs. Sure, the SUV has a bigger gas tank than the little Insight, but it also burns through that gas a lot faster.
Right, and so what's happening here in this example is you have a higher mass star, even though they're both low mass. And what we mean by low mass stars is stars, let's say, that have a mass less than about 8 times the mass of our sun when they're in the phase that our sun is in now, which we call
Right.
the main sequence.
Main sequence, right?
And in that phase, what's happening in the centers is that hydrogen is being fused into helium through thermal nuclear reactions. And that's the energy source ultimately that powers our sun and other stars that are in the similar phase in their lives
Right.
to our sun. So what could happen then is if you have a more mass than some other lower mass star, you need to support more of that mass from collapsing in on itself. You need to provide that extra pressure, if you like, internal pressure. And so you need to consume your fuel more rapidly
Right.
than a lower mass star. And because you consume your fuel more rapidly, it runs out sooner.
It runs out sooner.
So your whole lifetime as a star then is greatly accelerated. That is much smaller than when you compare it to a much lower mass star.
Right.
So getting back to the case with the white dwarf and the situation with these type 1a supernovae, if you had a white dwarf star, so a star that has gone through all of it, a low mass star has gone through all of its cycles, end up as a white dwarf and is prevented from further collapse due to this electron pressure.
Right.
If there was an even lower mass star that was nearby, let's say in orbit around now the white dwarf, maybe it's just finishing converting its hydrogen to helium in its core as a main sequence star. And one of the things that happens, it begins to expand outwards.
Right.
And if it expands enough, and if the distance between the white dwarf and this other star is short enough, then matter can be transferred from the expanding star on top of the white dwarf.
Yep.
And then what happens, Robert, if the white dwarf accumulates enough material that it raises its mass to be, essentially greater than 1.4 solar masses? What happens to that white dwarf?
A destructive explosion that we call a type 1a supernova.
Yeah, so the star blows up.
The star blows up.
And as far as we know, there's nothing left behind. I mean, the explosion occurs throughout the whole entire white dwarf itself.
Right. It simply can't support itself, so boom. It's kind of like trying to squeeze a balloon smaller than it possibly can. It'll rupture.
And so for what we're using these white dwarfs, these type 1a supernovas, in this case, is that we can use them, it turns out, to measure distance, which is, when you think about how do you measure distance in astronomy, right? You look up at the sky at night, let's say with a friend, and your friend says, you see that bright star over there? That star is about 8 light years away. In other words, if you could travel the speed of light, about 300,000 kilometers per second, it would take you 8 full years to journey from that star to make it to Earth. And of course, you look at your friend and say, well, how do you know that? It's not like someone went over there with a tape measure and wiggled the end of it when they got there and you look down to see how far away it is. There has to be some way of measuring distances in astronomy.
Are you wanting to get into the distance ladder?
Just a little bit, because we're going to run out of time if we go into it fully. But the idea is that there are different techniques that we use in astronomy to measure distances. And what we discovered was when these supernova type 1a blow up, the peak brightness, the peak luminosity, as we would say in astronomy, think of it as the wattage of a light bulb, the peak wattage, right, is the same from one type 1a supernova to another once you calibrate it for its declining brightness. In other words, its light curve, as we would say.
Right.
So the important thing for this discussion today is that we can use these type 1a supernovae to independently measure distance. That's the important factor here, within some precision, of course, some uncertainty.
Right.
Now, it's, if you like an analogy here, the reason why this works is because every white dwarf that goes type 1a supernovae has just exceeded this 1.4 solar mass limit, what we call the Chandrasekhar mass limit, named after
Subramanian's Chandrasekhar.
Yeah, and so he, from a theoretical point of view, he described what happens to these supernovae when they exceed this limit. So it would be like you had, let's say, 10 identical sticks of dynamite. They were manufactured exactly the same. There is no difference. They come from the same manufacturer. They are constructed the exact same way. You take each one of those sticks of dynamite, put them somewhere safe in a gravel pit or something, light it up, explode it, measure the peak brightness of the explosion, and then repeat that for all not the remaining 9 sticks of dynamite. So you had 10 explosions in total. And you should notice that if these sticks of dynamite were manufactured identically, one would expect that the peak brightness would be the same for every stick of dynamite.
Absolutely. I would expect that.
Now, for these type 1a supernovae, because the progenitor, that is, where did they come from, the body that was there prior to when they went supernova, to when they blew up, because they are essentially the same, roughly 1.4 solar masses, we expect the peak brightness, that luminosity, to be the same. At least you could calibrate it.
Right.
And astronomers have done that. In fact, that was done really well in the early to mid 1990s.
And in fact, we calibrated them against other methods of determining the distance to find out that, yes, they have about the same brightness.
Right. So now when one of these same supernovae go off in some distant galaxy, we know what the peak brightness is in terms of its luminosity, and then we can just compare it to what is the brightness that we actually measure, what we call the apparent brightness or apparent magnitude, because we use magnitude system here in astronomy, but we're not going to get into that for this discussion because we run out of time. And so we know that light falls off from these type of sources as 1 over the distance squared, which means if the brightness of your object is a certain amount that you can measure, if you double the distance to that same object, it would only look 1/4 as bright, 25% as bright.
Right.
Because the light falls off as 1 over the distance squared. From point of view of geometry, you can imagine the light coming uniformly from a light source like a star, filling up an ever larger volume of space. And you measure a certain little patch on that imaginary surface.
And it's the surface area of a sphere, which is
which
4
goes
pi r squared.
which goes like the radius square, or in this case, as we're calling it, the distance square.
The distance squared.
So the light decreases as 1 over the distance square. So by measuring, then finding, first of all, supernovae in distant galaxies, and we can do that by looking at its spectrum and telling it that it is a type 1a supernova, because there are other types that don't work as well for measuring distances.
Right.
We want this specific type 1a from white dwarfs as the progenitor. Then we can measure independently the distances to galaxies. And when we do that, we can then compare that distant measurement to what it should be based on the expansion history of the universe. It turns out that the further away a galaxy is, the faster it's moving away from us as the universe expands. And you can interpret that as the further away a galaxy is, the more space that lies between us and that distant galaxy. As space is expanding at a certain amount, then of course you can add up that contribution till you get to the distance of the galaxy and be able to calculate then how fast that galaxy should be moving away from us. So that's distance that's inferred from the expansion of the universe. And you can compare that to distance that's inferred from the observations of these type 1a supernovae. And what was discovered in 1998 is that those distances don't match. And the reason they don't match is because the universe has not been, expanding away at an ever less rate as time, that is decreasing
It's not slowing
rate.
down.
It's not slowing down with time. They discovered that the expansion of the universe has actually been speeding up. It's been accelerating. So the expansion rate today is getting greater and greater and greater with time, not decreasing as we naively expected it.
Which is just weird because it says something's firing it.
It's like you threw an apple up into the air, and instead of slowing down, it actually took off and sped up.
And sped up, yeah.
It's as if there's some other force that's pushing the apple away from your hand.
And that's what we named
Dark
dark
energy.
energy.
So the accelerated expansion of the universe, we coined the thing that causes it as dark energy. We don't know what it is exactly. We know what happens to the universe because of this presence of dark energy, but we want to be able to measure it as precisely as possible.
And we want to know what it is.
Yeah, ultimately, hopefully allowing us to determine, of course, what this dark energy is.
Yeah.
So since 1998, astronomers have been conducting various surveys using different techniques that have nothing to do with supernovae type 1a, all coming to the same conclusion that our universe's expansion rate is accelerating and speeding up, not slowing down. Now, the term, as we mentioned already, dark energy, that we use to coin that influence, whatever that is, if it's real energy or not, we don't really even know that, right? We just know that the universe's expansion rate is speeding up, not slowing down. So we try to measure it as precisely as possible using, as I mentioned, different techniques, including the original technique of using type 1a supernovae.
Mm-hmm.
So the dark energy survey itself was designed to measure a large area of the sky using various techniques, including using type 1a supernova. It looks at the formation of structure in our universe using galaxy clusters. It looks at other things that we call baryonic acoustic oscillations, which we do not have time at all today to talk about during this podcast, but we could talk about it in a future podcast. And looking at gravitational lensing effect as a way of determining the expansion history of the universe, to tell how much it's been increasing by, and so on and so forth, as we go back in time. Now, to be technical, more than, let's say, 5 billion years ago, so the universe's age is about 13.8 billion years old, that if you go back more than 5 billion years in the past, the expansion rate of the universe actually was slowing down. It was roughly about 5 billion years ago that it turned around and is now starting to accelerate.
Well, that's interesting in and of itself.
Yeah, and the reason for that is that the dark energy, if we want to think of that in terms, has a certain density. So per cubic volume of space, let's say 1 meter by 1 meter by 1 meter, there's a certain amount of dark energy that's in that volume of space.
Which is really weird in and of itself.
Right, and it's a very low value compared to what we typically would think of in terms of the overall density of matter, or maybe the overall density of light, of radiation. Okay, electromagnetic radiation is what we mean here. As the universe expanded, because the universe gets larger and larger, the density of matter gets less and less and less. The amount of matter gets spread over a larger and larger volume of space. The same with electromagnetic radiation. The density goes down. It decreases as that radiation gets spread over a larger volume of space and also gets redshifted.
Right.
That decreases then the density of that radiation. Well, if you have a dark energy, which is a different component altogether, if this dark energy density is an absolute constant, it will not change as the universe ages. It'll have a certain amount per cubic volume of space, and that amount will stay the same.
Okay.
Now, as the universe expands, both the density of matter and radiation decrease until eventually it's less than the density of dark energy. It's like all of a sudden dark energy becomes dominant. It drives the dynamics, if you like, or the expansion of the universe. And because it pushes things away from each other, unlike gravity, in some sense it works like anti-gravity, you want to think of it in that terms. That means that roughly about 5 billion years ago, the density of both matter and radiation dropped to the point where dark energy now becomes dominant. It has a greater value, and it causes the expansion of the universe to stop slowing down. It actually reverses it and causes it to speed up. And so for the last 5 billion years now, our universe has been accelerating in terms of its expansion, speeding up and speeding up and speeding up. Now, ultimately, what we want to know is what is that dark energy?
Right.
Has it really been an absolute constant for the whole history of the universe and going forward?
And if it has, what's generating it?
Exactly. All of these kind of wonderful questions that you can ask related to dark energy. Now, this result that we're showing here that was just submitted a few days ago is using 5 years of the dark energy survey data on about 1,635 supernova type 1a. Now, what they measured is that the expansion of the universe is continuing in a way that it's like a constant dark energy, what we call a cosmological constant, except in this case, it's a little bit less than what we expect. It's a little bit, so it's not a perfect constant value of the dark energy density for all of time. It seems to be changing. There was a little less of it earlier in the history of the universe than there is now. But that result is very, would I say, very loose in the sense that there's not a lot of supporting evidence for it.
Okay.
The evidence then, if you think of it, so in science we use the sigma stuff, right?
Okay, yeah.
So if you look at something that's really profound and sticks out, it may be, 10 sigma event that's happening, right? If you look at something that seems to be there, maybe it's a 5 sigma event, it's away from the expectation,
Right.
the value that you'd expect. This result shows that dark energy has been a constant for all of time, a little less than 2 sigma.
Okay.
Which means it's in that borderline area that maybe it has been changing the dark energy density, but maybe not. We don't really know.
We need more data.
You need more precise, more accurate data,
Yeah.
and that's what's going to happen here. So in the future, we'll be able to nail down this. It gives us some interesting perspective that it may not be an absolute constant. It may change with time, but don't bet anything on this yet. You would never use
Not
this
at 2
information.
sigma, I'm not.
No, exactly. It's almost like saying your hockey team today is going to defeat the team that they're playing, but there's only a 55% chance of that happening. Are you going to put $1 million on that bet?
Nope.
No. You want, at that point, probably a 99.9% chance is going to happen, right?
Right.
So this is like that, right? The chance of it not being a constant cosmological, dark energy, right? Cosmological constant. Is not that great, the significance. So don't bet on it yet. It's a little too close to tell.
And that's what I was looking at. This lower graph is basically comparing 3 different models of it and the best fit of the residuals. And basically all 3 of them fit the data. So which one is right?
Right.
I don't know.
So in order to get a better way of discriminating, you have to reduce those uncertainties.
Absolutely.
And that means collecting more data and hopefully maybe a better calibration of the distances and so on.
Which, how you determine that, the bars that are going vertically around the red and blue circles in that bottom graph are the error bars.
Right, the uncertainty.
The uncertainties. So you want those as small as possible. And as you can see, the error bars touch all 3 possibilities.
Now, there's an interesting sort of historical connection with wanting to have a cosmological constant, an energy density that doesn't change.
Yeah.
And that involves Einstein. So when Einstein came out with his general theory of relativity in about 1915, 1916, one of the things when people applied his equations of general relativity, a modern description of gravity, in other words, to the universe as a whole, they came up with the idea that the universe either had to be expanding or contracting. It can't be stable and static.
Yep.
But Einstein would communicate with the astronomers at that time, and they would tell him, no, Einstein, the universe is static, even though your theory predicts in that sense that it should be expanding or contracting. And it was roughly about 10 years later that we discovered, no, the universe is not static, that it's actually expanding.
Right.
But in the intermediate time, Einstein actually stuck in a fudge factor, as we say, in his equations of GR, general relativity, to make the universe static and not be expanding or wanting to contract. And he called this, eventually it was called this, the cosmological constant, the lambda
And
term.
he ended up claiming it was his greatest mistake.
Yeah, because, a little over 10 years later, all of a sudden we discovered that you didn't have to have that cosmological constant. That fudge factor was not needed, wasn't required. Right. And therefore, why put it in? And so he regretted that decision of adding that. He could have made a bold prediction that no, astronomers are wrong, that the universe is either, you'll find, in a state of expansion or contraction.
Right.
In some sense, he would have made one of the greatest predictions of all time when you think about cosmology. Or
been one of the great predictions demonstrating general relativity.
Yeah, and it's amazing when you think of somebody's brain can come up with this stuff, and it actually applies to the universe as a whole when you think of it that way, to reality. Now, so that's kind of the simplest type of dark energy, is the one like Einstein where it doesn't change the energy density at all with time. And it seems all the results up to this point point to the fact that is the type of universe we live in. But if it isn't, it's just a little bit off. And that's kind of what this result is showing, that maybe there's evidence here that it's not quite a cosmological constant, that the dark energy does change in terms of its strength with time. But like I said, the data is so iffy here in terms, because of the precision is not that great, that we just don't know. And that's fair to say. And that's actually reflected in the next slide if you want to bring it up.
Okay, I'll bring it up.
And in this slide, we're looking at various models, and the thing to focus on here is the right panel. And you can look at, for example, the top part of it says the DES, that's Dark Energy Survey, Supernova 5-year data, with no reliance on anything else. And what we're looking here basically is under the W sub A. That's like the second column from the far right. And if you look down, there's different values that you get there. If you go, that's how W would change with time, its rate of change with time. But if you go one column to the left, so the third one from the right, that's the first order sort of effect of the cosmological constant. And notice that the top value is minus 0.80. Now, and there's an uncertainty there, both on the plus and minus side. And notice that it's minus 0.80. If our dark energy is an absolute constant, that value should be minus 1.00. It's not quite minus 1. It's minus 0.8 with some uncertainty. But that uncertainty, the range of those error bars, each of those errors are 1 sigma errors, as we say in the industry
I'm
here.
not going to bet anything on
No,
that.
so the difference from minus 1 to minus 0.8 is less than 2 sigma.
Right.
Now, is that profound? Is that really telling us that it's not quite minus 1 and therefore not a perfect constant with time, the dark energy, in terms of its strength? The answer is no. The data is still imprecise.
Imprecise and inconclusive.
Yeah, we still need more data to try to narrow down those error bars, to make them smaller, to see, once we get up to the order of 5 sigma difference, then we say that's significant. In fact, in particle physics, you would never claim a discovery unless it's about a 5 sigma significance. So the Higgs boson, they detected that several years ago, and when that reached, I think the actual significance came out to be like 4.9 sigma. That was enough to say, yeah, we got it. Since that time, of course, they accumulated more data.
It's up to about 6 sigma.
Yeah, the significance is a lot greater now than 4.9. So you're at about 5, round it off if you like, where you make a discovery, right, an announcement of this. This is less than 2.
Right.
So it can be totally consistent with the cosmological constant, with that which Einstein invoked, those many years ago.
All this discussion of sigma says we probably need to do at least a partial show of statistics and what we mean when we say sigma.
Yeah.
But that's another show. So
right. So those are familiar with statistics. We're talking about Gaussian statistics.
Yes.
Right. The bell curve that we know and love.
Yep. That happens anytime you have randomly sorted data.
Right, and you assume there's no correlation.
No correlation, no connection. Where one changes the other.
Right.
Yeah.
So these results will become better as we accumulate more data and even combine it with other methods and so on. And that's kind of what we see there when you go down that table in that slide. For the second section there, you're combining it with measurements of the leftover heat from the Big Bang. That's the Planck data. And you can see it tightens up those uncertainties. Now we're down to minus 0.955. So it's becoming more consistent with the -1. And then there's other things that you add there. If you go down a little bit further, for example, you combine it with the Sloan Digital Sky Survey Baryon acoustic oscillation data plus year 3 dark energy survey data, and then another one down below when you combine it with essentially everything. And we're up to values, that's starting to reach -1, but we're still, a couple sigma away, essentially, right? So we really need to continue this exercise. We're not quite there to say if it's exactly -1 or not.
Right.
Right. So we'll see. I mean, that's for the future. So that's kind of a good rundown, I think, and a lot of what's been going on lately. And there's lots of other things that
there's other things that have been going on.
Yeah, you just don't have time to discuss. But these are kind of the main ones that we thought people might be interested in us talking about and so on. Now, if you are interested in science, if you're interested in arts, if you're interested in any sort of higher education and learning process, come here to the University of North Dakota, both on campus, and we do have courses that you can take online if that better fits your situation. And the rule of thumb, of course, Robert, is never stop learning.
Never stop learning. I'm taking a class this semester myself, so, yeah.
And you're only 20.
I'm only 20. No, I wish. I wish I were only 20.
Now, our next podcast will be a week from today, so that's January the 23rd at the same 3 p.m. Central Time.
Mm-hmm.
And we always leave you with a quote at the end of it all.
I haven't heard this one today.
You haven't heard this quote? By the way, this quote is fittingly from Albert Einstein.
Okay, cool.
And it's related to the cosmological constant.
Excellent.
So here's what Einstein supposedly has said. Now, when we always say quotes, I'm never 100% sure that's actual quote from that person or that's made up along the way or misattributed to somebody else actually said it. Yeah. And other people got the, they're the ones that get, the benefit of it today or whoever, right?
Right.
The attribution of it all. So this supposedly is something that Einstein said. And he said, quote, "Since I have introduced this term, the cosmological constant, I had always a bad conscience. I cannot help to feel it strongly that I am unable to believe that such an ugly thing should be realized in nature."
Wow.
So Einstein didn't like it.
He didn't like it.
Yeah. With that, thank you very much for watching. Don't forget to give us a thumbs up and a like. Subscribe to this.
Subscribe.
channel.
Ring that bell.
Yeah, ring that. Do all those things to try to increase our awareness that people out there actually enjoyed this podcast. Feel free to make comments even after the fact. And we'll see you next time. Thank you very much.
See you in a week. Have a good night, folks.